the whatever the ejected electrons will be seen from photoelectric effect, these things will call it as photoelectrons. If any frequency is, the normal frequency of light is less than threshold frequency, there is no ejection of electrons. Whatever the spectra we have seen here, that is in between the specific wavelength and also with dark spaces we can see. Hello everyone, welcome back to the session of Structure of Atom. I am Harshita Bhavsar from Vidhyaashram PU College, Temple of Excellence. We'll see what we have seen in the last class about what we have discussed. That is developments leading to the Bohr's model of atom, wave nature of electromagnetic radiation and characteristics of electromagnetic radiation and particle nature of electromagnetic radiation. These things what we have discussed and what we have understood from the previous session. So today we are about to discuss, that is photoelectric effect and problems about regarding photoelectric effect and dual nature of radiations and different kinds of spectra. So we'll see first what is photoelectric effect. So Hertz, he is a chemist, he accidentally found this effect. So what does it effect means? Hertz discovered that when beam of light of certain frequency strikes the surface of some metals, electrons are emitted from the metal surface. This phenomena is called as photoelectric effect. And the ejected electrons are called photoelectrons. When he is telling that, he told that already, like when the light, means white light or any kind of light with a frequency hit the metal surface, this is the metal surface. See, this is the metal surface. When light is hitted or directed on metal surface, at the time of hitting, the electrons will be ejected or emitted from the metal surface. So that metal surface will be detected here. Okay, these electrons are negatively charged, so we'll call it as electrons. This is vacuum chamber and this is metal surface and this is light directing towards the metal, and this is a detector where the ejected electrons will be detected in this instrument, and this is ammeter and connected to overall battery. This is the photoelectric effect completely how it has been instrumented here they have shown. Okay, whatever the ejected electrons will be seen from photoelectric effect, these things will call it as photoelectrons. Okay, since electrons name, they are negatively charged. Next we will see the further observations and results of the photoelectric effect. When a photon of sufficient energy strikes the electron in an atom of the metal, it transfers its energy instantaneously to the electron without any time lag or delay. Means when the light is directed to the metal surface, without any time delay or a lag of time, the electrons will be ejected towards the detector. Next point, the number of electrons ejected is proportional to the intensity of brightness of light. Means we are producing, or in the experiment they are producing light. If it is a yellow light they are producing, that time electrons will be ejected. That we know already. See, if they increase the intensity of light, intensity means if they increase the brightness of light that produced already given light, if they increase that yellow light, that time automatically the number of electrons ejected will be increased. Ejection of electrons will be increased when the increase in the intensity of brightness of light. Okay, thus we can tell that number of electrons ejected is proportional to the intensity of brightness of light. Okay. Next we will see the threshold frequency. It will be designated or denoted as nu naught. For each metal there is a characteristic minimum frequency below which photoelectric effect is not observed. Means every metal having a certain frequency, okay, certain characteristic minimum frequency is there. If it is below that minimum characteristic frequency, the ejection of electrons will not be seen. That minimum frequency what it has been there or what it has been allotted or what it has given to that metal where it will be characterized, that frequency will call it as threshold frequency. Okay, this is called threshold frequency. If frequency of light is less than threshold frequency, means if any frequency is, the normal frequency of light is less than threshold frequency, there is no ejection of electrons. Okay, threshold frequency is the minimum frequency where the metal will respond to the ejection of electrons. If normal frequency is less than threshold frequency, then there is no chance of ejection of electrons. Another case is there at a frequency, like our frequency, that metal frequency is more than threshold frequency. See here, when frequency is more than threshold frequency, the ejected electrons come out with certain kinetic energy. Means when frequency is greater than threshold frequency, the ejected electrons come with certain kinetic energy. So, kinetic energy of these electrons increases with the increase in frequency of light. When the frequency of light has been increased, that time ejection of electrons will be increased. Automatically, the kinetic energy of the experiment will also be increased here. Okay. Since the striking photon has energy equal to h nu, means E equals h nu, and the minimum energy required to eject electrons is h nu naught, means that is threshold frequency. This is E equals h nu naught is threshold frequency. Then h nu minus h nu naught is equal to the kinetic energy of the photoelectron, that is half mv square. This is kinetic energy, half mv square. Therefore, h nu minus h nu naught equals half mv square. Okay, where m is the mass of the electron and v is its velocity. This is the overall gist for next what we are going to see one formula. Energy of incident photon, threshold energy plus kinetic energy of electron, means energy of incident photon. Whatever the incident photon, it will be having some energy. That energy of incident photon will be equal to threshold energy. Okay, equivalent to threshold frequency what they have seen, that it will be same as threshold energy plus kinetic energy of electron. How it has been ejected of electrons, that kinetic energy will be equivalent to threshold energy. Both will equivalent to energy of incident photon. We know that E energy is equal to h nu. That is a common formula what we have seen in this previous session. See here, h nu equals h nu naught plus half mv square. Okay, we can write again like this. Kinetic energy equals h nu minus h nu naught. This equation, how it has been came through previous slide, we have explained how the kinetic energy will be given with formula. Kinetic energy is equivalent to half mv square. So, we can write it in this way, half mv square equals h into nu minus nu naught. We have taken h is common here and nu minus nu naught. So, nu is frequency of the incident light, nu naught is threshold frequency, m is mass of electron. See, the minimum energy required to eject electrons, it needs some energy, right? So, overall photoelectric what function it needed, complete photoelectric work function. So, it needs some energy, that energy with relevant to function will call it as work function, that is h nu naught. And these formulas what we have written, it will be useful for your next problems or numericals what we will solve. Here we will see some of the problems based on the photoelectric effect. Calculate energy of 1 mole of photons of radiation whose frequency is 5 into 10 to the power of 14 hertz. Okay, they have asked how to calculate the energy of 1 mole of photons having the frequency is 5 into 10 to the power of 14. They have given frequency, we have to find out energy. We will see the solution. Energy of one photon is given by the expression E equals h nu. We know that E energy is equal to h nu. They have used this formula. H, this is the constant, Planck's constant, that is 6.626 into 10 to the power of minus 34 joules, right? And frequency they have given here, that is 5 into 10 to the power of 14 per second. And energy H nu, we are implementing this into this formula, 6.626 into 10 to the power of minus 34 into given frequency. We will get this much of joules, that is energy, and 1 mole of photon, this is 1 mole, 6.022 into 10 to the power of 23 is equivalent to 1 mole, right? So, they have asked for 1 mole of photon. So, we are multiplying with 1 mole of photon with what we get energy with multiplying with the given 1 mole of photon. So, we will get 199.51 kilojoule per mole. Okay. This is a simple problem. And next, the threshold frequency nu naught for a metal is 7.0 into 10 to the power of 14 per second. Here we have to calculate the kinetic energy of an electron emitted when radiation of frequency, that is 1.0 into 10 to the power of 15 per second when it hits the metal. They have given already frequency and also frequency and threshold frequency they have given. We have to calculate the kinetic energy. We will see here frequency, here 1.0 into 10 to the power of 15. Threshold frequency is 7.0 into 10 to the power of 14. These things they have given. According to Einstein's equation, kinetic energy equals half mv square equals h into nu minus nu naught. This is frequency, this is threshold frequency. Again we are solving to this formula. 6.626 into 10 to the power of minus 34 is h, that is Planck's constant, and frequency, see here that we have taken here minus, this is threshold frequency, this is frequency, and this is threshold frequency, this is h. Okay. Here again we are calculating 6.626 into 10 to the power of minus 34. Before that we have to equalize this one. When we are subtracting the powers, it should be equivalent. See here 15, 14 is there. So, we have to be reduced for both the 14 only. So, we are converting here. So, we will get 10.0. By that, we will get 14, 14 equivalent. After that, we will subtract 10 minus 7 is 3. 10 to the power 14 is common. Later, we will multiplying the Planck's constant into the calculated frequency, will get 1.988 into 10 to the power of minus 19 joules. Okay. With every problem, we have to write the units. We have to end up the solution with unit, or else we cannot expect the complete marks in the numericals. Unit is very much important. Next, dual nature of radiation. We have seen already light or a radiation, electromagnetic radiation will act as a wave-like nature and also particle-like nature. Here also we are telling the same with respect to light. Okay. Light has dual nature, that is wave nature as well as a particle nature. When it will show as a particle or a wave-like nature, it acts like a particle when interacts with matter. When light is interacted with matter, it will act as a particle. When it propagates, it will act as a wave. Okay. Spectrum, we will see spectrum. When solid substance is heated, it emits light. When some solid substance is heated, it will emit some light. If this light is passed through the prism, dispersion takes place and series of color bands are obtained. When some of the solid is heated and it will emit some light. We know that. Okay. When it emitted light, it will pass through the prism. Okay. After passing, the light will start dispersing. Why? What is that dispersion means? Dispersion is splitting up of bands. Okay. The splitting up of series of color bands we'll see after the dispersion. Okay, that phenomena we'll call it as spectrum. We'll see the different kinds of spectrum here. First we'll see the continuous spectrum. What is the continuous spectrum? The spectrum of visible light, which consists of all the wavelengths, is called continuous spectrum. See here is a white light passing through the prism. Okay, after light means it will be already heated up. After passing the prism, it is getting to dispersion, or it is showing the different colors of series of color bands here. See, looking above these bands, it will look as overlapping with merged color bands. Means one by one, there is no gap in between. So, we'll call it as continuous spectrum. And this continuous spectrum will be having all the wavelengths, all the frequencies and all the wavelengths will be having completely WEIGHTAGE region, means violet to red. That is visible region in the electromagnetic spectrum. So, violet to red region, overall visible region we can see here. The spectrum of white light that we can see ranges from violet, that is 7.50 into 10 to the power of 14 Hertz, to red region, that is at 4 into 10 to the power 14 Hertz. This is the continuous spectrum containing with its range. Next we will see the emission spectrum. Whenever electromagnetic radiations interact with atoms and molecules of matter, the electrons in these atoms may absorb energy and jump to a higher energy state, losing their stability. See here what will happen. Completely, when electromagnetic radiation will interact with matter, after interaction, the electrons in this atom may absorb energy. Okay, it will absorb energy. Later, it will get into excited. If we take hydrogen here, it will be having some electron, right? And it is again having some orbitals, correct? This electron will excite it to the, or will reach to the higher energy level. That higher energy level we will call it as excited level, correct? Excited energy level. See, whatever once the atom or electron has been reached to higher energy level, it will not stay in the same level. It will come back to the original state. Whenever it coming back to the original state, it will emit some energy or radiations. Okay, it will emit some radiations whenever the electron coming back to the original state from higher energy level, that is from excited energy level. That emitted energy or that emitted radiation will be seen in the spectra. Okay, will pass through the prism and will check into the overall spectrum. In order to regain their stability, they need to move from the higher energy state to more stable energy state by emitting absorbed radiations in various regions of the electromagnetic spectrum. Whenever it will reach, it will not in the stabilized state. So, to reach the stabilized state, it will come back to its original state. So, how the radiation, what radiation it will emit? Already it has been absorbed when it is reaching the higher state. So, that absorbed energy will be emitted. That absorption, emission of radiation, will call it as emission spectra, where we can see the overall lines of spectra. This spectrum of radiations emitted by electrons in the excited atoms or molecules is known as emission spectra. See here, excited sample, already it has been excited. It is coming back to the prism. It will detect in the detector, and here it will reach in the emission spectrum. Here we can observe the overall emission spectrum. Whatever the emitted radiations will be seen, here we can observe. This is about emission spectra. And these things will be seen in the gaseous molecules. That's why we have taken the example hydrogen. Next we'll see the absorption spectra. It is like the photographic negative of an emission spectrum. It obtained by the absorption of certain wavelength by a substance from the electromagnetic radiation to which it is exposed. To better understand these things, see here, white light, we are passing through some sample. Here also we have take as a gaseous sample. We are passing here through sample, and after passing through sample, it will reach prism. Between that, sample has been absorbed some of the light. Okay. Whichever the light are not absorbed by the sample, it will reach the prism. Next, it will reach the detector. Overall, we can see in the absorption spectrum. In between, we have seen this dark lines. Whatever the dark lines we are seeing here, black lines. Why it has been spotted means some of the energy lines or some of the radiations has absorbed from the sample. So, that lines are seen in the spectrum as dark lines. Okay. The missing wavelength which corresponds to the radiation absorbed by the matter and leave dark spaces in the bright continuous spectra, that is known as absorption spectra. Once again I am explaining. See here, white light is passed through some sample. If it is a gaseous or anything, that sample will absorb that radiation. Some of the radiation will not be absorbed through this sample. That will pass through prism and it will detect it towards detector, and it will be absorbed on the continuous spectrum or absorption spectrum. In that bright absorption spectrum, you will be seeing some black dark regions. Why it has been dark region? What it corresponds to means, it will corresponds to the radiation absorbed by the sample or matter what we have used here. That is known as absorption and about emission spectra. Next, line spectra. The emission spectrum of atoms in the gas phase emits light only at the specific wavelengths with dark spaces between them. Whatever the spectra we have seen here, that is in between the specific wavelength and also with dark spaces we can see, and it will be in the lines of spectrum in overall spectrum region. That's why we are telling emission spectrum of atoms in the gas phase. We have seen in the emission spectrum and absorption spectrum in the gas phase only emits light only at specific wavelength, okay, with dark spaces between them. Such spectra are called line spectra, or also we can known as, it will be known as atomic spectra. Line spectra is also known as atomic spectra. What is the significance of line spectra or atomic spectrum is, each element has a unique line emission spectrum. It is showing specific wavelength and each element will be having specific line emission spectra. Every element cannot show in as a previous element what we have produced there. So, hydrogen will be having separate line spectrum, any other nitrogen, oxygen will be having separate line spectrum. The characteristic lines in the atomic spectra are used in the chemical analysis to identify unknown atoms. If we doesn't know the what element we have produced in the gaseous tube, by seeing or observing the line spectrum, we can identify which element has been produced inside the gas tube by seeing only its spectrum, line spectrum. In the same way as fingerprints, like we know how the fingerprint representation we have seen in the forensic, like that here also to identify the unknown or element we can use this line spectrum region. Next we will see about line spectrum of hydrogen. In your syllabus we are considering about only line spectrum of hydrogen, that's why we are seeing here. When electric discharge passes through gaseous hydrogen, the hydrogen molecules dissociate and energetically excited hydrogen atoms produced emit electromagnetic radiation of discrete frequencies. See here, our hydrogen will be written as H2, it will dissociate, means dissociate, it will break, correct. Hydrogen will be having electron Okay, that electron will want to be excited and it doesn't want to be in a same excited level, so it has to be reach out the ground level, that is original state. That time it will emit some electromagnetic radiation of discrete frequencies. When it is coming back to higher energy level to original state, it will emit some radiations. Not only one kind of frequency we can see, there we can see the different discrete frequencies. Okay, those frequencies will be named off by their discoverers. Okay, these lines grouped into 5 series. Frequencies, this is on lines, these lines are grouped into 5 series. After that emission of light, they have to pass through the prism, their dispersion will take place. After dispersion, several series we can observe there. Those series will be named based upon its discoverers. We'll see Lyman series, Balmer series, Paston series, Brackett series and Fund series. Here P is silent, so we'll call it as Fund series. These are the 5 series what we can observe from the line spectrum of hydrogen. Why we have given this region means Lyman series will be end up of UV region, Balmer series in visible region, Paston series in IR region, that is infrared region, Brackett series again infrared and Fund series in infrared region. So we'll see again here the line spectrum of hydrogen. See, this is the overall orbital picture. This is the nucleus and this is the orbits. See here, electron will move to the excited level and reaching up again to the first level. Okay, like that. Balmer series are already excited, but it will reach only to N equivalent to 2, that is second energy level. Likewise, similarly, Paston will reach to N3, Brackett N4, Fund N5. Okay, it will not reach, every series will not reach end up to the original state. It will reach one by one before ending to the original state. That is how we have shown here. See, with allowed electron energy levels N equal to 1, 2, 3, etc. It may be so many orbitals or orbits we can observe here. This is the line spectrum of hydrogen, overall line spectrum. See here, N may be 1 to 6 or it may be extra infinite also based on the molecule. This is only the picture of line spectrum of hydrogen. Not only it will correspond to all the elements, it will be correspond to only hydrogen. That's why N may be so much also. Okay, again here see Lyman series all will reaching to N equal to 1 and N equal to 2 is Balmer series, all will reaching to N2 and Paston series is N3, Brackett series is N4, Fund series is N5. These are the series. This is the energy level. Okay, this is the overall series of atom. We'll see the Rydberg equation. Wavelength of any spectral line in any series of hydrogen spectrum can be calculated by using Rydberg equation. Okay, Rydberg is a scientist name. He has given this equation based upon the wavelength of spectral line in any series of hydrogen. In any series of hydrogen, by using wavelength, we can use this equation. That equation we'll call it as Rydberg equation. This is 109,677 is a Rydberg constant into 1 by N1 square minus 1 by N2 square per centimeter. Okay, where N1 equals 1, 2, 3, 4, 5, 6, anything etc. maybe. N2 equals N1 plus 1, N1 plus 2, N1 plus 3, N1 plus 4, like that. See, this is the series where N1 will reach here, N2 spectral region. Lyman series will be the spectral series will reach first region and the corresponding next regions will be 2, 3, 4, etc. and spectral region will be in ultraviolet region. Next, Balmer series. Second, that is N2. N2 will be 3, 4, 5, maybe extra visible region, like that Paston 3, remaining 4, 5, 6, and it will be reached in infrared region. Bracket series, Fund series is a 4, 5 respectively, and 5, 6, 7, etc. and 6, 7, 8 both will seen in a infrared region. These are the overall things about spectral lines or line spectra of hydrogen atom, and all the elemental spectral regions are not similar. That's why we are again and again we are telling these are spectral lines are about only hydrogen. Okay. In next session, we'll see about Bohr's model of atom, explanation of line spectrum of hydrogen, quantum mechanical model of the atom. Thank you. We'll see in the next session for the remaining things.